Welcome to qnawire.
All right, so for this problem, you are dropping a tennis ball on top of a basketball, and this thing hits the ground, and then the basketball rebounds and still hits the tennis ball again on the way up. So essentially, so we can have two situations before the collision and then after the collision. So what we want to address first is the situation just after the collision, in which this basketball is now moving upwards with a certain velocity, and this tennis ball is now moving again downwards. So I've separated them here to make it slightly easier to understand, because essentially what happens is, first, the ball is going to hit the ground and the basketball is going to hit the ground and then start moving upwards, but the tennis ball is still going down. So essentially, these will be this will look like the scenario just after the collision with the ground, but before the collision with the ball. So essentially, we can assume that this is mass M, small m, and this is mass big M for the basketball. So this is right before the collision, and then after the collision, you have a situation where essentially this basketball is going to have a certain velocity going upwards, and then this tennis ball is also going to have a certain velocity going upwards as well. So this is small m, this is again big M. So notice that the only things that you're given here are essentially, they tell you that this thing falls through a height h, and they tell you the ratio of the masses, and they don't tell you anything else. So whenever we have, so we can assume here that this collision happens really fast, which means the impulse is very small. So this, the velocity of this ball is going to be the same velocity that it had going downwards. So we know exactly we can calculate exactly what that is in terms of h, should we need to. But essentially, this is an elastic collision where both kinetic energy and momentum are conserved. So if we want to know the initial velocities and the final velocities, we can use those two equations. So we can assume, in this case, I can set up my coordinate system to say that upwards is positive and downwards is negative. And I can assume that this, since this is falling down, it has a velocity v. But notice that the velocity doesn't depend on the mass. So if it falls through a height h, it means that this velocity of the ball is also v, because the velocity is just a function of the height. So it's just 2gh because of conservation of kinetic energy. So given that, we also need equations for the initial and final velocities for elastic collision. So if you write out the momentum equations, which say m1 v1 initial plus m2 v2 initial, this is equal to m1 v1 final plus m2 v2 final. And the kinetic energy equations will also be half m1 v1 initial squared plus half m2 v2 initial squared will be equal to half m1 v1 final squared plus half m2 v2 final squared. So now you have these two equations, and these you can combine and simplify them into expressions for the velocities of these things. So we know that if we work on this algebra, we'll find that v2f is actually equal to 2m1 over m1 plus m2 minus m1 minus m2 over m1 plus m2 multiplied. So this is multiplied by v1, and this is multiplied by v2. And these are the initial velocities. So anything I have over here are the initial velocities, over here are the final velocities. And then for v1f, I have also the similar expression, m1 minus m2 over m1 plus m2 plus 2m2 over m1 plus m2 also multiplied by v2. So these equations come in directly if you go ahead and simplify these two equations together, you come up with the expressions for these. So notice now that if we go back to our diagram, we can actually simplify this a little further. So we'll call m1 can be the mass of the basketball here. So I'll call this m1 and I'll call this m2. And so that means that v2 is velocity of the ball, of the tennis ball after the collision, and v1f is velocity of the basketball after the collision. And then these will be the initial velocities. So now I can plug in my numbers to see what I get. So again, the other thing that you need to notice here is that we can assume that the mass of the basketball is much larger than the mass of the tennis ball in this case, because this is a symbolic calculation. You don't need to come up with exact numbers. We just want an idea of where this tennis ball is going to go after this collision. So now with this assumption, and you know the velocities in this case, we can now go back and see what that's going to give us. So for v2f, we can now, so since this is 2m1, which is the greater mass, and m1 plus m2, since m1 is much bigger than m2, this essentially just becomes 2m1 over m1 times v1, okay? And then this would be minus, so since this is very small compared to this becomes m1, and then this is just, again, m1, because m2 is very small. So this would be minus v2. But v2 is v2 initial. So v2 initial is actually pointing in the negative direction in my sign convention. So this velocity is actually negative. So this would be minus v, essentially, or minus v1, because these things have the same velocity magnitude. So I can just call that v1 in this case. So you notice that this becomes 3v1. And v1, again, is just the square root of 2gh. So we'll notice that if the velocity of the tennis ball is 3 times the initial velocity of the basketball, given that the velocity is directly related to the height here, if you increase this by 3, if you multiply this by 3, then you also have to multiply everything else by 3. So essentially, if you now go back to the equation that gave us this height, we know that mgh is equal to half mv squared. So that's where we get this from. So this directly leads to that. But notice that if the mass doesn't change, if you're moving at velocity v, you essentially are going to achieve a maximum height of h. But if you're now moving at a velocity 3v, since this velocity is squared here, you're actually going to end up with a maximum height of 9h, because this should be 3 squared. So if you Now, so if I'm now moving at 3v here squared, which should now be equal to mg, let's say h2 here. So if I now want to find the ratios, I can divide these two equations. I'll find out that my height after moving with this increased velocity is actually going to be 9 times the initial height that I had. So essentially, after this collision, this ball is moving at 3 times the velocity. This tennis ball is moving at 3 times the velocity. And because of that, it achieves a maximum height of 9h. So it's going to go much higher than the initial height that it had. So you can also go back here and try to calculate what V1 final is going to be. And you will see that again, since M1 is much greater, this just becomes, so I need a V1 here. So since this was much greater, this is just going to be M1 over M1 times V, which is just V1. And then if you are dividing something very small with something very large here, essentially your whatever you get is going to be very close to zero. So essentially, the velocity of the basketball after this collision is going to be pretty much the initial velocity that it had here, which is v. So the basketball moves with the same velocity upwards, but the tennis ball afterwards is going to go with a velocity 3v1, or 3v in this case, and the basketball is going to move with velocity 3, and the maximum height is h. So the reason this goes even much higher is because, again, the energy is still conserved because we neglected the action of the ground here, but the ground causes a change in momentum, and at the collision with the ball again, there's a change in momentum because this is a much heavier object. So this will impart some momentum onto the tennis ball, which means it's going to go much higher than it did before.